Okay. So for number 18, it says use vectors to show whether or not the points form vertices of a parallelogram. Then they give us some points. Either they do or they don't. So you can kind of guess and see what it gets to. But Russell suggested just plotting points, right? And that would work okay too. If you use one of those point plotters online to go through and plot the points, you should be able to kind of see what's happening, and that would be okay. Or a way we can do it without just plotting points more algebraically requires some more parallelogram. So what do we know about parallelograms?
They're going to have 4 sides.
They're quite they have 4 sides. What else?
And two sets of parallel sides.
Right, yeah. So if we can figure out of these points the vectors they make, if we have 2 sets of parallel sides, then we should be able to know if we have a parallelogram or not. So how do we know if vectors are parallel? So we can just get our multiples of each other there. The other thing that we can do, because if you think about this, not are those 2 vectors going to be parallel, but they're going to be equivalent, right? If you scale those both to the origin to their component form, you're going to have the same vector there because they should be the same length too. So why not even see that scalar multiple? We should just see the same vector showing up here. Now, I still probably would go back and graph it just to see which points to start with, because looking at these 4 points, it's like, I don't even know which 2 should try to connect there. So let's do that. Let's graph it. I'm pretty sure I have this link on our Canvas page. Double check there. I think I put it under modules. Under class information or course, yeah, class information, there should be a link for a 3D grapher, and that brings you to the GeoGebra thing. So if you don't want to type it yourself, it's there. Okay, so the points. We use these points: 1, 1, 3, -2, -3, 10. Oops, negative comes first. There's 2 points, and now so we can see the other one. There it is. 0, 0, 3, 3, 4, -4. All right, so there are all 4 points that we are working with here. And again, if you can just look at a graph and make sense of this, that would be okay here. So if we try to line it up this way, do these look like they're all in one plane? Yeah, and that's important because if you have like 3 points on the plane and then 1 floating above the plane, it's not really going to be a parallelogram. So they have to be kind of flat. We're talking about 2-dimensional shape there. So by that, it looks like it's okay. And this is all just looking at it visually here. If we try to line this up, I'm also good at this part. That's kind of hard to see too. If we try to line this up so we're looking flat on there, if we imagine connecting A to D and C to B, those look like they could be parallel, right? And then across the other way too. So if that's sufficient and you want to base your answer on that, that's fine, but we'll still go through and take a look at the math here. But this does make it look like A to B should be one vector and then D to C should be another vector. Okay, so let's check those. So A to B is first 2 points, and then D to C is the last 2 points. So let's check that. A, B, B. And we know how to find component form. Okay, terminal minus initial. So if we go through and do this, A to B is going to be -2 minus 1, so it's -3. -3 minus 1 is -4, and 10 minus 3 is 7. And if we go from D to C, 0 minus 3 is -3, 0 minus 4 is -4, and 3 minus -4 is 7. So we get the same thing there.
So does it have to be component form?
No, you.
Oh, I guess. I mean,
it's probably easiest. It doesn't have to, but it's probably definitely easiest to be in component form.
No, I was thinking about just doing it 2 points, but I can't do that.
Well, you kind of can. So if you imagine taking that one and kind of moving it up to the other one, like adding and subtracting it, it's doable, but it's probably not as efficient. So yeah, it's probably better. But another good thing to look at is if I would have reversed C and D, would I still be able to tell if these 2 things are parallel? So if I would have instead found D to C, what if I would have done this? So I would have subtracted those backwards. So now I have 3 minus 0, 4 minus 0, and -4 minus 3. Does that still work in answering this question?
Yeah.
Sure. Okay, going back to the scalar multiple thing. A vector can go this way, a vector can go the opposite way. They can still be parallel to each other here. So whether you found DC or CD, you're still going to be able to see the vector. In this case, you're just multiplying it by 1, so it's kind of boring. But that would definitely show that those things are the same vector, they're equivalent. And then if we were to go back and check the other 2, I'll graph real quick. Okay, so going from A to D and B to C, we should see the same type of thing there. Okay, so again, if you just can look at the graph and kind of visually figure it out, I'm okay with that. It shows you're understanding it. Or algebraically, we're kind of picking points. And the graph does help make the picking process a little more efficient there. But you can just randomly pick points and see what happens. It'd be a lot more work to do it that way. But yeah, that's what we're looking for. Okay. So yes, I'm gonna make a parallel here. All right, 17. Let's do the one notes before we get back to question 17. I think that should answer it without too many troubles. It's basically the same thing like the one in the notes, so we'll just do the one notes there. Okay.
I just want a question on 5, but we can do that.
Let's go see what 5 was real quick.
It was like what we did in the notes, but it was like backwards.
Okay, and we'll come back to this one in just a minute. Okay. All right, so, and then I guess I should ask Stephanie or anybody in Stewart, do you guys have any questions at this point? Besides obviously the ones we didn't cover yet?
Okay, so when you graph a vector with the initial point at origin, wouldn't you just graph the point and have it connect to the origin?
Yep.
Okay, I just want to double check on that one.
Exactly. Edwin, did you find anything in your notes you wanted to ask about?
No, please.
No, not right now. Okay, if that changes, let me know. All right, so page 12, oh, page 11. Let's do that one first there. So we just talked about, and we reviewed this a little bit, that thing we ended with last time was talking about points, vectors being parallel means they're considered multiples of each other. And we just mostly did a lot of stuff in 3D here. Deciding points are collinear. First of all, what does collinear mean? They're on the same line, right? So in two-dimensional space, it's fairly easy to do. You can just like find an equation and then see if the third one fits. But in three-dimensional space, that's harder because there's an infinite amount of lines and planes that we can be sitting on here. So points being collinear, they're going to be in the same plane too. That'll work out also. But we're just looking at that line right now. So how can we figure this out? How can we decide if these points are on the same line? Without having an equation for a line, because those get complicated in 3D. We'll talk about that later.
Subtract all 3 and make them part of a point form.
Yes, that's, I would say, instead of trying to touch all 3 at once, we can something like that. So if we say take P and Q and find what vector those guys make, and then say, okay, well, let's find maybe QR or PR, any other combination. Exactly. If we get parallel vectors, then we know they're all going to be collinear here. If you want to start off by graphing these, that would be okay too. I mean, you can maybe obviously see if they're not, but algebraically, that's exactly what I would do to check these things. So let's just do that.
But if they're parallel, they can be parallel but shifted. And they wouldn't be collinear, right?
That is true. Okay, now you're making me think more, because I was just going to do the first way you said. Let's start off by looking at a graph.
Would it be possible to have, P and R parallel, but not all of them be parallel? When I look at I mean, not parallel, collinear.
Let's do this. So there's the first point. This. See, every now and then it spins. Now I don't know what I'm doing to make it spin, but there we go. Okay, so there's the first point. Second point is 2, 1, 0. Okay, so if we just look at these things, does it look like we're okay and they're collinear?
Yes.
Yeah, right? Kind of looks like we can line them all up. There we go, we can see they all line up there. So again, just visually looking at this, yes, it looks like they're collinear. And so when we go through and check to see if they're parallel, we will, but still to address what you said, if one of these points is off, well, I think it'll still be okay. Because really what we're doing when we find this component form, and let's label these what it actually has in the book there. What's the first one? P, Q, and R, right?
I mean, if we get it from P to R, and then Q had to be on the line, or
right, so
Q
yeah,
is a perfect scalar, that would work.
Right, and that's basically what we're looking for here. So I think as long as we show that their component forms
with long, long, and short, but I don't think we do PR or PQ to QR. Because that can show the QR.
Well, I mean, if you think about R as a starting point, though, then wouldn't that still be okay? So instead of thinking about P as a starting point, if R is a starting point, I think it would still be okay. I think I see what you're saying. I'm not clear as to what you're saying, but I can't figure out how I want to explain this. Let's do the math part so we can show this one works, and then I'll think about it some more. Okay, so looking at the graph, yes, it looks like they're collinear. To check it is, let's go ahead and check the vector. So let's check PQ, that's from the top point to the middle. Then let's check PR. So if we find component form 2 minus 1, I haven't been showing the work, but I'll write the work here. 1 minus -2, and 0 minus 3. So that gives us 1, 3, -3. So basically the idea is if I took that PQ then and put it at the origin, like Stephanie said before, from 0, 0, 0 to this point, we're going to have that vector. And if we check the last one, 4 minus 1, 7 minus -2, 6. And are those guys scalar multiples?
They are.
Yeah, so we can see that if I multiply this whole vector by 3, I'm going to get that other one over here. So we're good. So we know that these two things are parallel. Well, here, let me do this, because I can't think of what I'm missing. The homework question has something similar. Let's say if they do anything additional.
I think it's like number 18 or 19.
Okay, so here's that same, nope, this one here. Here's the same type of problem, but in homework, determine the points are collinear, we're given 3 points. They are collinear. So there's the same thing, PQ to QR. They showed it was a scalar multiple, and that's it. They stopped there. Which is what I expected. But I see what you're saying about, like, how do you know that they're not just parallel vectors? You know, oh, because one of them started at the same point. We're guaranteed that P has to start at that same point there. So as long as P is going to be fixed at that point, if it's collinear, if it's parallel to another vector that starts at the same point, they have to be on that same line there.
Yeah.
So like if we had like one set of points, and then a different set of points, and we were trying to
That's
show
what I
that
was
collinear.
thinking.
Yeah, and that's why I was confusing in my head, so I was picking that. But no, since we know they have to start at the same point, if we know they're parallel, it has to be collinear. Yeah,
Yeah.
okay, well, good.
We won't get the 4 points yet.
No, we're not going to do that. Well, hopefully the rest of you guys on the video get what we just said there, but this is sufficient. What we just did here is all we have to do, because since we're guaranteeing they all start at the same point, as long as they are just scalar multiples of each other, we know they're going to be collinear. One just starts at Q or stops at Q, and then we kind of move on to get to R. So are these points collinear? Yes.
I don't understand. How are they collinear? What does collinear mean?
So collinear means they're all on the same line. So all these points lie on the same line there. And if we look at this graph, we can kind of see that, right? So there's those 3 points. And it looks kind of like P, Q, and R are all lining up on the same line. They're free to draw a line through them. So what we checked was if we go from point P to point Q and we make a vector.
Right.
Okay, that vector has a direction or component form of this guy right here, the 1, 3, -3, right?
Right.
Then we say, okay, well, let's make another vector that goes from P all the way through that point to R. Since they both have to start at the same point, if the vector PQ and the longer vector PR have the same direction, so if they're scalar multiples, we know that we have to pass through Q to get to that, so we know there's collinear. And that's what we showed here. So starting at the same point P for both of them, on one of them we just went to Q, and that's what this guy is telling us right here. And on the other one, we went through that point, and we just kept going through to R, just a longer vector of it. So since these are scalar multiples of each other, we know those 3 points had to be on the same line there. So if
Okay.
we take PQ and we multiply that vector by 3, that's where we get the other vector. And because of this, we know they have to be collinear. Does that make a little more sense?
Yeah, it does.
Okay.
All right. Thank you.
And one thing too, you're not going to be able to just plot points when you're doing these things on the test here. So going back and starting with something like this, sure, it helps in class. That's not going to be something you can just do on an exam. So understanding what it means to be collinear and be able to kind of picture what's going on here is going to help here. And if you didn't know, you should check PQ and PR. You can still go back and do different combinations of points, kind of like we saw on the one we just done the homework. You're going to get scalar multiples of each other, so it might not be multiplied by 3, it might be multiplied by -3 or something like that, and that's fine. As long as you can show that there is some scalar that exists that makes this true, then that's really what we're looking for. But
So if
like,
there's scalar multiples, that means they're parallel vectors.
exactly. Yep. So as long as you have any number you can find here, since we know they're starting at the same point, whether you start at P or you start at Q or you start at R, as long as you have any number that makes a scalar multiple, you know this is going to be okay. I just picked the ones that match up with the picture. Okay.
I just have another homework question.
Okay.
When we're going the unit vectors,
Mm-hmm.
and then it's asking for in terms of I and J.
Mm-hmm.
Which one's I and J? X is I, right?
It's alphabetical. Yep. So X comes before Y, I comes before J. So I goes to
So-
X and J goes to Y.
Component form was, let's say it's just 3, 1.
Okay.
It'd be 3I plus 1I, or 1J.
So you're saying if the component form is 3, 1, this would be, say it again?
It'd be 3I plus 1J.
1J, so just plus J.
Wow, so why am I getting them wrong?
I don't know. I can go back and look at your problems. I should be able to see what you're typing in there.
Dude,
So it's saying my component form is correct, and then it's saying for the, it's asking for,
Are you entering just an I on your keyboard, or are you making sure it's that bold I or that vector I?
Oh, yeah, you have to do that, right?
Yeah, because if you just type I, the computer says you're typing variables, but we want to know that it's a vector. So I don't know what there should be. Well, let's pull it up. It's probably going to apply to more than this. Yeah. Lots of times there's written shortcuts you can use,
right,
and I don't know what the written shortcut is for that one. But if nothing, and I don't know which number this is. If nothing else, you can use the little thing that comes up on the side. So when you start typing, it brings up this little shortcut thing over here. You go down to vectors, there are the default vectors right there. You just click the buttons. Otherwise, you can do something like this to make anything a vector.
gotcha.
So, but there should be shortcuts for all of them. I just don't know what the shortcut is for that one.
I gotcha.
So
It
That's
looks like you
probably what's
don't, it looks like for component form, you don't have to put the real bracket.
sometimes it already have the weird little brackets there for you. It kind of types some of the information that you need.
I'm just gonna put it in the normal parentheses.
I'm just doing whatever those.
Greater than, less than signs?
Yeah.
Okay.
I mean,
That's what I
it
would
has
do.
to work. I didn't know parentheses.
Yeah, okay, we'll just,
I guess I'll
Okay.
just do parentheses.
Good questions. These are things that I don't really get to do unless students ask questions about those problems. I'm glad you guys bring it up. Okay, but what I thought you were going to mention was the next thing we have to cover here. So talking about standard unit vectors in space. So page 12, last thing of 11.2, and then we'll go back to whatever homework questions we have left and whatever time we have. Okay, so Russell was just talking about standard unit vectors. We have I and we have J that we talked about in 2 dimensions here. And the vector I is just that little component form 1, 0. It's just going 1 unit on the positive x-axis. Then vector J is just going 1 unit on the positive y-axis, like we see here. So if we now have 3 vectors, or 3 dimensions that we're talking about, we're going to go through and modify those a little bit, but we really need to have our 3 standard unit vectors. So any guesses as to what our 3 standard unit vectors are in 3-dimensional space?
I, J, and K.
They are I, J, and K. That is true. So I corresponds to going in the x direction. What do you think the component form for this is going to look like?
1, 0.
Not just 1, 0, but 1, 0, 0, right? Because now we have that z component too. We're not going anywhere in the z direction. So 1 unit in the x direction, nowhere in the y direction, nowhere in the z direction, this. Which means our j vector doesn't go anywhere for x.
0, 1, 0.
You got it. And that means k would be what?
0, 0, 1.
Exactly. Okay. So those are going to be our 3 standard unit vectors for 3 dimensions. But all the same things we had before that we said with 2-dimensional vectors still work. This is an alternative way to go through and write out our vectors. Sometimes component form is nicer, sometimes this linear combination form is nicer, but you should kind of be comfortable with both of them. If you prefer one or the other, that's fine, but make sure that you're comfortable with both of them here. Now, one thing that's going to show up more with this than we saw with 2-dimensionals is missing a component, just because there's more things to what we do. So for example, in this vector here in number 8, we're missing a j component, right? So when we go write this in component form, what's that going to look like? What's the change in the x direction right now?
4,
And the y direction?
0.
0. And then the whatever, -5. Okay, so when you're missing that component, you don't just skip it in component form. It means there's a 0 there. It means there was no change in that direction. So again, you can kind of see maybe when some of these would be more useful than others. It kind of depends on what we're doing with them, but they mean the same thing. Those are two equivalent ways to write that same vector there. Okay. Find the terminal point. Example 9 says find the terminal point of vector v, given that the initial point is that one given there. So when we are given this, okay, we don't have to work with it in component form, but just to get a little bit more practice here, what would this look like in component form?
7,
-1 and 3.
Yep. Okay. So now we have component form or standard unit form. Again, work with whatever one makes more sense to you. But really, this wants to know what's the end point. If we're starting at this point, -2, 3, 5, and we're using this vector, what's going to be our terminal point? How can we figure that out?
We have to add them.
Now we're basically going to add the two things together, right? So this starts at the origin. If we imagine it just telling us a set of directions, we're just going to apply those directions to this point P. So to find our terminal point, we'll call it Q since the book often does. We know that we're going from that point -2, and then we're adding 7 units. We're going positive 7 units in the x direction. From that point 3, we're going to go 1 unit backwards in the y direction, and then positive 3 in the z direction. So 5, 2, 8. This probably is not something we're going to do a whole lot. We don't usually care about where the terminal or where the initial point is, but it's good to just understand these vectors are just sets of directions. That's really all they're doing. They're saying, okay, from somewhere, do this. And when you start off with the origin, the directions can be much simpler because you don't have to account for any right movement so far. So that's really all this is the point of this is. It's just to say, okay, just be comfortable understanding what these mean. This actual process isn't really going to be all that useful. And last one, just to show, again, the parallels between the two of them. And I'll give you guys just a minute to do this on your own. Find the magnitude of that vector, and then find a unit vector in the direction of B. And though it doesn't say to write a component form or standard linear form, whatever you want to write that unit vector as is fine. But take a minute or two to go through the algebra on that one, and we'll see if everyone's right.
Just some of the back, the components. Or each of the components.
Yeah,
Type YouTube. I always put an L at the end of YouTube when I type it. I don't know why. All right, let's see what you guys came up with. Murillo, what'd you get for the magnitude of this vector?
radical 62.
Everyone else the same thing? Okay, and then so then how do we find a standard unit vector? What do we do? Radio, we can take that component form divided by magnitude. So we have 7 over root 62, or 2 over square root of 62, negative 3 over square root of 62. You could also write this as just 1 over square root of 62 times component form. I wouldn't advocate this one. I think distributing is better, but that isn't wrong. You could do it that way. If you want to write it as a linear combination of the vectors, you can do it that way too. So you can write it as 7 over root 62 in the I direction, plus 2 over square root of 62 in the j direction, minus 3 in the k, and that would be fine also. So all of those are equivalent. You can go through and write it. If you want to write that linear combination in factor form, go for it. That's fine too.
Can you just quickly explain what the unit vector is again?
Sure. Yep. So those unit vectors are, let's do this. Let's just grab them.
That concept is
That's fine. That's okay to ask about. Oh, it doesn't do that.
Yeah. This is standard. Yeah. Standard, yeah, standard for I, J's, and K's.
I thought that's how I graphed vectors yesterday. Why do different?
Yeah, it's the same thing. Standard form. This one not the I, J's. And this is component. And that is it. Like that's what I said. I was going to say you have to find it. Put it in the terminal. Like,
White apples?
how many rights have we gotten so far? 6. Oh, wow, this goes quite a ways.
What am I doing wrong? We did this before, right? I did successfully plot a vector on this before. Okay, I guess it has to do with parentheses and parentheses. Okay, so that little black line right there, that is the standard unit vector in the x direction right now. And my graph is set up to be a left-handed system. I don't want it that way. I don't know how to fix that, so we're just gonna deal with it. But that little black line right there, that's just one direction in the x direction. But like I said, right now my system is set up backwards, so I don't know how to fix that quickly. If we go through and do vector, I'll name it j. Vector j then is going to be a similar thing. It's going to be just one unit in the y direction. We have this one little vector that makes right there. And then our last vector, k, is one in the x direction. And so if you think about these three little vectors, they're basically just kind of making like the corner of your coordinate system there. You're saying 1 unit, 1 unit, 1 unit. And then what we're doing is using the properties of vectors to be able to add, subtract, and multiply. We're stretching and shrinking these guys, flipping their direction, and they're really just a way we can describe how to point to a different vector there. So there's like 3 different simple directions, saying like north, south, east, and west, that kind of thing there. Saying we'll go this far, and then put them all together there. But the actual standard unit vectors just make these little shapes there. They're just, okay, 1 unit in each of these directions. Is that kind of answer?
Yeah.
Okay.
So if you were to find the magnitude of these points, would it be 1 of the one we found the unit?
Yep. Once you've got that unit vector, you can find the magnitude of this one. And you can real quick check when you go through and square each of these components here. So if we were going to find, they call this u instead of v, that may make it better too. If we were going to go through and find the magnitude of this, which it didn't ask us for, but we can do it. So we'd have the first term squared plus the second term squared plus the third term squared. And if you add together those numerators, this gives you 62, which divided by 62 is 1. So yeah, it'll just give you a magnitude of 1 there.
So I'm seeing find unit vector and standard unit vector.
Same thing. So the standard unit vectors are always going to be similar things. Okay. A standard unit vector are those I, j, and k. So it's 1 unit in the x, 1 unit in the y, 1 unit in the j.
Don't have to do the magnitude on the bottom.
But yeah, because they are just unit vectors. If it says standard unit vector, it's still a unit vector, so it has to have magnitude of 1. Okay. I'm not sure that answered the question you said the second time though. So like unit vectors are this bigger group. They don't have to be standard unit vectors, but all of our standard unit vectors will definitely be unit vectors. Does that make sense?
Because the homework is kind of worried on that too.
Yeah. Whenever it says a unit vector, we're generally starting at the origin, just going somewhere with a length of 1.
Okay.
When we have a standard unit vector, we're still starting at the origin, going somewhere with a length of 1, but that somewhere has to be either 1 unit in the x, 1 unit in the y, or 1 unit in the z. That's it. So when you put that standard in front of it, it's forcing it to be those 3 little vectors, and that's all. Is that maybe? Okay. When you have homework questions, feel free to send them to me. There is a way within WebAssign you can email me questions about the homework. I don't know exactly where it is. I know like what my math lab is.
Top right of the question.
Okay, is it for each question there? So I don't know if there's on each question where it's set, but feel free to click that and I won't show it on
right.
mine.
Yeah, right where it says that.
Yeah, so on mine it doesn't have it there, but I mean, I'll try my best to get back to you quickly. The reason why it's more helpful to click that link than just say I have a question on whatever number is if you've got weird numbers, I can see what you did, I can see your numbers. If you've already entered something, I can go back and see your answers. So like when it's I instead of the vector I can tell you that kind of stuff there. But yeah, let me know. So if there's something that you think should be working, it's not, just send me an email. I'll figure it out. Okay. Okay, but I think that was it for the notes, right? Yeah, so that's the end of 11.2. We're not going to start 11.3 today. 11.3 today gets into document multiplication, and the better you understand this part of it, the easier the multiplication piece will be, because that's a little bit more abstract. Multiplying vectors is a bit more complicated there. So, were there any other homework questions, or did we kind of hit everything at this point? Okay. And how about Stephanie and you guys in Seward, whose names I'm not always going to say, it'll just be the Seward guys, sorry. Do you guys have any questions on the homework?
No, not yet.
Not yet. Okay, same thing. Send me emails over the weekend if you do. It's due Sunday by midnight. That practice sheet, I think right now. So that PDF practice sheet I emailed to you guys and just handed out here, that's not for points. That is simply just more practice, different types of problems. Some are going to be similar to homework, some are going to be different, but just more practice on this kind of stuff here. Ideally, if you sat here and had time in class to work on math questions, I'd be able to kind of come around and help you guys out with it instead of just having to wait for the homework to try it. But I know that not everyone wants to sit here and do more problems, so there's for points there. So generally what I'll do is hang around, work on it. I can kind of help you guys over the computer for it, or you guys can help in class. But I'm going to post the answers on Canvas after class. So if you do work through them, you can go back and check your work. And I have the work shown with it, not just the answer, so you can kind of see the process of going through it. But it's just simply for more practice. Again, it's not for points. I don't need you to turn it in. I'm not going to call you up to the front of the class and ask you to go over it. Just the setup doesn't really work for that very well there. But I will point out on that sheet, it goes over section 11.1, 11.2, just like the homework, everything we've covered so far. It's pretty much chronological, or goes in order of how the sections go too. I would say if you want to just try at least like the application problems, so like questions 4 and 5 and 9, those are probably the most difficult just because it's not just doing the algebra, it's the application. So if you feel comfortable going through the math with it, then just try those problems. If you don't feel comfortable going through the math with it yet, then I would say don't worry about those right now. Go back and try the ones that are just saying find the magnitude, find the unit vector, and that may kind of just give a little extra practice. The other thing is, and I'm not going to take time in class to show this right now because I don't know how the sound is going to work, but there was a little video in the notes that I had linked to before. And if you're curious and want to watch it, it's pretty entertaining there. It's just called vector addition. So I just searched Japanese vectors, cars, and this came up here. Or kept linking those. But anyway, if I just skip ahead a little bit so you can kind of see what's going on there. They basically have a truck set up with this gun, not this gun, this, what do you call it? Ball launcher. Ball machine, right? That's going to pitch the ball basically, and they're measuring the speed. And they have a car. They're trying to cancel out the two vectors there. So it's pretty interesting to watch and see what happens. But they get all excited and they talk Japanese, and they've got this little, you can actually see the little truck they're driving.
Oh, I know.
Got this like dumpy little truck there. Yeah.
Shot a cannon on that.
Exactly. So the truck's going this way, and they're trying to shoot the cannon going the other way and see what happens with the ball. Yep. And so it's pretty neat. So if you want to just skip to the end and kind of watch what happens with it, it's kind of fun. But it's also cute to listen to a bunch of Japanese guys that are super excited to talk Japanese too. So anyway, that link is in there. It's just trying to show that vector addition does how when we're going one direction, the opposite direction, they cancel each other out there. It's just kind of fun. So feel free to watch that if you get a chance. Like I said, if you guys want to hang around now and work on that sheet, go for it. I'll be here to answer questions. Otherwise, just if you've got time and you need extra practice,
Do you say you're going to post the answers on Canvas?
Yep, I'll put them in again, not on the Seward County Canvas, but on the Garden City one, the one I actually have access to. But yeah, I will post them on Canvas. I'll kind of show you where. Oops, not that one. No announcements. So when you guys go to the Canvas page, over on the side where there's modules, I did add the blank practice sheet, so there's just a PDF of what I handed out to you guys if you didn't get the email or whatnot. But then right underneath here, I'll just add 11.1, 11.2 key. And I'll just upload a PDF file and we'll have that there. And if Canvas is, I mean, hopefully it works out okay, but if the Canvas is too difficult or annoying to get into, I can email you guys the files too, if that's any easier, but I will put them up here. And also, I've been trying, because Cole's missed class the whole week, and so I've been recording lectures. I'm still trying to figure out an easy way to get those videos available. I think I can just upload them all to YouTube, and that's fine. I haven't had problems with that yet. But eventually, I'll put the lectures here too, from days people missed. I won't record every single one, but if I know you're going to miss, I'll try to do that. Just another option to kind of get caught up. Okay. So, anything else for you guys? All right, like I said, feel free to hang around and work on stuff for the next 20 or so, 15 minutes, but if you're good to go on a Friday, I'm not insulted if you leave. I'll just assume you practice on your own sometime.
I just have a quick question on two, because that's like almost the exact same problem that was.
Well, that, this one.
So we have the unit, the magnitude of the vector, and that's the unit one that I'm struggling with how to get.
So we can go over right here. We know that we want this vector in here to be 5 units long, right? And we know that this is the vector we're trying to mimic here. So right now, if this vector already is 5 units long, we're just 1. So if we go from 0, 0, negative 1 to we're 5 units per page, but it's not. So what we can do is, okay, we basically need to scale this vector to have a length of 5, is really what it comes down to. If we find this unit vector between 0 and 0, the benefit of the unit vector is no unit vector is length of 1, really easy to stretch or shrink 1 to whatever.
Yeah.
So if we find the magnitude of this, and then create a unit vector in this direction, we're then going to take that unit vector and just multiply by 5.
Okay.
So it's kind of like a long one.
Okay. So, and so we know that
This is from the book. U doesn't always mean unit vector. In this case, U is a unit vector.
it's not a unit.
Right. And that's what the book is sloppy about, that it uses U and V interchangeably. But this is not the unit vector right now. It has a length of something longer than that.
Oh.
It turns out to have a length of square root of 5.
Okay. So it's square root.
For the most part, our book has pretty good notation, but every now and then it does something weird like this, and it shows up later on too. It uses row to do 2 different things.
Yeah.
Miss Nicole?
Yes.
Okay, so on the practice question number 1, like how do you verify that has a length of 1?
Basically just find the magnitude. So once you go through and find a unit vector, you're going to have something divided by whatever you found for that length. Take that new unit vector and just find the magnitude of that. When you go through and plug that unit vector into the regular distance or magnitude formula, you should get an answer of 1. Right? Because so for that first one here, you get that the length of v is 5 times the square root of 2.
Right.
Yeah.
And then so you then take that vector v and divide both those components by 5 times the square root of 2. And so that new vector you get is pretty ugly, decimals all over the place. But if you take that new vector and find the magnitude of that, you should get a 1 out of it.
Oh, okay.
So yeah, anytime it says verify, it's just like prove it to me. Actually find it and make sure it's actually doing what it's supposed to do.
Okay. Sounds good.
That worked out. Right.
Things. So then you just so you get the unit vector, then you just multiply by 5.
Right, because we know that unit vector has a magnitude of 1. And so since we want this one, so another way you can go about doing it is just switch those 2 things together. We're still going to go back and find this. It's in between step. We know that we can just scale it, and if we multiply just the original thing by 5 over square root of 5, that would come too. And this is just kind of breaking it down. That makes more sense with that little pause here. Yeah, it's kind of an awkward problem. The way it's worded, and using U for both of them doesn't help either.
I think that was the same problem as 5.
I think it was too, and I forgot that you mentioned that that was one you had a question on. I'll pull it up real quick and see. Find a vector, you have the same type of thing there. I accidentally screwed them, but yeah, that should be the same. So, same idea.
work on these.
I think what's most confusing at this point isn't so much what we're doing, it's just like the words that get used.
Yeah.
Because like if you think about it, it's like, oh, it's just adding numbers, that's simple. But it's like, well, which ones do I add and when do I add them? So it's
Yeah.
just new terminology that makes it a little
Yeah,
challenging.
the concepts aren't too bad, it's just figuring out
And
what they mean by
The whole class will be that way too. The concepts never really get too bad because it's things we've already done. It's just, yeah, when they're asking for it and understanding, being able to picture it and stuff like that. Hopefully as we work more, it'll start to make more sense.
Yeah, I think it will too.
Most students are the same way. In the beginning, they're kind of like, and then they're like last semester, I had one student tell me the class was easy, which kind of made me feel bad because it shouldn't be easy, but
Yeah.
he was also a very bright person. So it'll work out. You guys are good at asking questions so far too. That helps
Yeah, I
also.
think, questions.
Yeah. Well, questions help me too, so I kind of know what I'm explaining well and what I'm missing. Keep asking.
Thank you very much.
Yep. Enjoy your weekend.
You too.
We go one home. Yeah, I had a square root of one and a square root of one.
You get this?
Well, I wrote it in decimals. I don't like fractions. I changed it to decimals.
Whenever you do this, you just put this in the line.
I don't do that. I just put everything in the calculator and just get the answer real quick. I'm not going to simplify that. Yeah, I just put everything in the calculator and just put it in decimals. Because I'm not gonna be working on those fractions.
Yeah.
And then change it to decimal.
Yes.
Yeah, you have to do one by one. If you don't do that,